Hello my dears, very good morning to all. So what we studied in the last class? So we studied some theory regarding the MI type instrument and its scale and all, its torque equation, okay, where we use MC and where we use MI type instrument, etc. Right? So today we are going to do some important problems regarding those type of instruments. Okay, write a question, my dears. We already started one question, right? One or two questions we already did. So very important question we are going to do now. Okay, write a question. Find the reading of PMMC and MI instrument. Find the reading of PMMC and MI instrument. This is the waveform, ideas. Okay, listen my dears. So we have to find the readings of the PMMC and MI type instrument. So before that, so let me tell you one thing. PMMC always read the average value, my dears. Average value if DC is positive. Okay, and MI type instrument always read the RMS value, my dears, if pure AC positive. If in PMMC instrument, if you pass mixed AC and DC, then also it will give the average value. In MI type instrument, if you passed mixed AC and DC, it will read always the RMS value. It will read always the RMS value, my dears. So these things you have to always keep in your mind. Okay. So in MI type instrument, we can pass both the AC and DC, of course. In MC type instrument or PMMC type instrument, we only pass DC. We can't measure AC value by using MI type instrument. So by keeping all this in your mind, find the reading of the PMMC. Let's focus on PMMC first. PMMC instrument first. So I already told you PMMC instrument always give the average value, right? If DC is positive, or even if you pass AC, then also it give the average value, correct? Even if you pass the mixed AC and DC, then also it give the average value. So in short, it always give the average value. So in this diagram, what is the average value, which is equal to what? Area under the curve divided by time period. Am I right, my dears? So there are two methods for finding average value. Either you can take 1 by t integral 0 to into v of t into dt. That method you can apply. But that integration again consume a lot of time of yours, right? So a better method is simply the graphical method, or the shortcut method we can use here. So area under the curve divided by time period. What is the time period here? It is 3. So let's see the area. Area means, see, I can divide this into so many rectangles. So this is first, the second and third, right? So first area will be 1 into 2 plus second area will be again 1 into this length is 1 length into height 4 plus third area will be again 2 to 3 again 1 into height will be 6 whole divided by what, my dear? Time period is nothing but 3. So it will become 2 plus 4 plus 6 divided by 3. So it is equal to 4 volts. If it is in volt means it is in current, right? It is current. So it will be ampere. 4 ampere will be the average value. Is it clear? Is it clear, my dears? Very easy, right? We already did some problem regarding this type of average value concept, so it is very easy. Okay, and next we have to do the RMS value. RMS value. RMS value. Again, we have a trick to find RMS value. It is very popular trick. It's very interesting also. So there are two methods. Of course, you can apply for the RMS value. It is nothing but 1 by 2 pi or 1 by t integral 0 to t into v of t square dt. This method you can apply, you can integrate, but it consumes again a lot of time for getting the RMS value. But there is a shortcut that I will tell you. The shortcut is nothing but first we have to find the squared waveform. First we have to find the squared waveform. So how can we find the squared waveform? Means we don't want to change the time. The time is a constant here. We don't want to change the time. It doesn't affect the time, my dear, but it only affects the magnitude. That is the meaning of squared waveform. Let's see that. So time, it doesn't change, so it will be omega t. So 1, 2, 3. Okay, there is no change in that. Squaring the magnitude, first magnitude of 4. So 2 becomes squared means it becomes 4. 4 becomes squared means it becomes 16. 6 becomes squared means it will become 36. Same, draw the same curve, my dear. Same curve. Okay. So this is the squared waveform. This is the squared waveform. Now, what is the RMS value equation? RMS value is equal to root of area of squared waveform whole divided by what, my dears? Time. How can we find area of the squared waveform? Now you forget this waveform. Your focus is only on this waveform. This is the squared waveform. So it will become 1 into 4 plus 1 into 16 plus 1 into 36 whole divided by time is not changed 3 whole root, right? So it will become root of 1 into 4 plus 16 plus 36 divided by 3. So 20 plus 56, right? Root of 56 by 3. Root of 56 by 3 ampere. So this is the answer. This is the answer. It's really interesting. You can find, it's have a very good applications where you can easily find any RMS value of any waveform. Area of squared waveform. Suppose you are start integrating this, no? You have to find the equation for both. You can by integration process also you can find the answer, but it is not that much easy, na? It consumes some time, right? So within some minutes, no? Within some seconds you can solve by using this shortcut. So this is a wonderful shortcut. So learn it. Okay, it will be definitely useful to you at the time of examination. Okay, so did you get the concept, my dears? So area of squared waveform divided by time period root of will be give you the value of RMS. So we found the value of what? So this RMS value will be the value given by the MI type instrument. Okay. That also you write on top. Okay, MI type, that is the RMS value. PMMC, that is the average value. Okay. In question we have for find the R not RMS and average. It is indirectly given as find the PMMC and the MI type reading. So PMMC always give the RMS value, sorry, average value, and the MI type instrument always give the RMS value. That distinction you have to know, my dears. Okay. Let's do another question. Okay. Find the reading of again a PMMC and MI instruments for the wave. Again you have to find the same RMS and average value of same you have to find. Okay, how can we find? How can we find, my dears? So this is a sawtooth waveform, correct? So this is a sawtooth waveform. Okay, so first we have to find PMMC reading. PMMC reading or average value. PMMC reading or average value. So how can we find the average value? Again, average value is equal to area under the curve divided by time period. So what is the area of under the curve? So this is a simple triangle, right? So area under the curve, time period is what, my dear? At what place or what time the signal is repeating is called the time period. Am I correct? In previous question, after 3 seconds only the waveform start repeating, but now after 1 second it will repeat. The same replica is again after 1 second. So this is nothing but, my dear, the time period. So this is nothing but the time period, which is equal to 1 second. Okay, so area under the curve will be simply what? Half B into H. Area of the triangle will be half B into H divided by time period is again 1. So 2.5 ampere will be the what? Average value. So it will be the I average. It will be the I average. Okay. Next you have to find the RMS value. MI reading or RMS value. So listen, my dears. So you have to find the squared waveform, right? So what will be the squared waveform? What will be the squared waveform? See, if you square this sawtooth waveform, you will get a parabola. So right here, squaring of sawtooth gives parabola. This you have to remember, okay? This you have to remember. So the waveform is likely to be like this. It is not sawtooth, but it is parabola. There is no changing time period and all, but the squaring will happen. The squaring will happen so that the peak value will become 25. The peak value will become 25. Is it clear? And the area of parabola, my dears, area of parabola, you have to remember this. It's equal to 1 by 3 into B into H. 1 by 3 into breadth into height. That is the area of parabola. So what is the RMS value? RMS value equal to root of area of squared waveform. This is the squared waveform and its area will become the parabolic area, that is nothing but 1 by 3 into B into H whole divided by, my dear, time period. So it is again 1. So the answer will be 25 by root of 25 by 3 ampere. You can take a 5 by root of 5 by root 3 also you can take. Root of 25 by 3. Okay, so that is the answer. Did you get the concept? Did you get the concept? Did you get the concept? Simply you have to go for the area of squared waveform and you have to find the value, right? Okay, there is not that much difficulty there. There is not that much difficulty. Can I rub this? Can I rub this, my dears? Write another question. Two, one. Okay. How can we find? Again, same question. Find the reading of PMMC and MI instrument. It is very important question, my dears. At least you can expect one question from this. There is a chance for asking such type of question. What is the reading of PMMC and what is the reading of MI type instrument under this curve? That type of question you may expect. How can we do that? So first of all, PMMC. So it will give the average value. Correct? But correct? It will give the average value. So average value will be, what was that? Area under the curve divided by time period. Am I correct? So area under the curve will become triangular. Triangular is simply half BH, half into B into H. Rectangular, it's simply B into H. Plus again a bigger rectangular, it will be again this rectangle, it's simply 1 into 2. Whole divided by time period. Time period is nothing but, see, started here like here and comes here. Again the same thing is repeating. So time period is nothing but, my dear, this much is the time period. So this is the time period 4. So if we solve this, 0.5 plus 1 plus 2 whole divided by 4. So it is nothing but 3.5 by 4 ampere. This is current means 3.5 divided by ampere. Okay, 3.5 by 4. Is it clear? Is it clear? Okay, so that is the PMMC reading. Then what will be the MI type instrument reading? MI or RMS value? MI or RMS value. So what will be the RMS? How can we find the RMS value? We have to square the waveform, correct? We have to square the waveform. So first I can directly going to write here, because or you want to square the waveform, you can directly write here, no issue. So squaring this will give you what? I will write here, RMS value will be equal to area of squared waveform divided by time. Is it correct? Area of squared waveform divided by time. So that will be the RMS value, which is nothing but, my dears, area of squared waveform. Let's find that root of this is the sawtooth, right? This is the sawtooth waveform. So if you square this, it will form the parabola, and the squaring of 1 will begin again in 1. So area of parabola will be what? 1 by 3 into b into h. So 1 by 3 into b into h plus, again this is a rectangular. If you square this, again 1 into square means 1, then 1, and length also 1. So 1 into 1 plus, again this is a rectangular. Again if you square this, 2 square means 4. So again 1 into 4 whole divided by what? The time period again 4. There is no change in that. So it will become root of 1 by 3 plus 1 plus 4 divided by 4. So it will become 5 plus 1 by 3, 15 plus 1, 16 by 3, so it will become 2 by root 3 ampere. 2 by root 3 ampere. How beautiful the question is, see how beautiful the question is, and how we arrived at the answer. It's that much easy if you really know the concept. Maximum this type of waveform you can expect for your examination, not beyond very high level, right? Not beyond this level. Okay, focus. Can I rub this, my dears? Next topic, extension of ammeters. Another important topic in measurements, extension. Because see, these are the topic where the questions are frequently asked. These are the sessions where. So what is the meaning of extension, my dears? What is the meaning of extension? See, so this is our normal ammeter having a specific meter resistance of Rm. It can carry a current up to Im. Okay, in our hand there is an ammeter, so which can carry a current up to Im. Im is nothing but its full scale deflection. Okay, Im is nothing but its full scale deflection. Im is nothing but its full scale deflection. Rm is nothing but meter resistance. And suppose there is a situation, see, in measurement purpose any situation can arrive, right? There is a situation in which we have to measure a very high value of current which is very higher than Im. In practical case, suppose we have 0 to 5 ampere ammeter. Suppose you have to measure, there is a situation, you got a situation in which you have to measure 25 ampere. So by directly using this 5 ampere we can't measure this 25 ampere, correct? Because it's machine, this meter having a certain rating, that is nothing but is 5 ampere. So beyond that 5 ampere, if you pass beyond that 5 ampere, that meter goes damaged. That means the meter will burn, because this much current it will not carry. So what we do? For every purpose or for every such a situation we have to change the meter. Is it possible? No, because the meter cost is very high. The meter cost is very high. So at every instant or at every situation, we have to change the meter for measuring this much variety of current is practically not possible. So what we have to do at that time? So what is the solution? So there we found a solution called extension of ammeters. Yes, extension of ammeters. So extension means, which is nothing but, suppose this is the meter current, this is the maximum current into meter carry. So extending means, we have to extend the ammeter, what we are going to do, we have to simply add a parallel resistance called RSH, so that it can total carry a very big current I. The meter always carry Im, and this current will be I minus Im. This current will be I minus Im, and there is nothing but V. So how can we extend ammeter means, simply we have to add an additional resistance in parallel with the meter bus. The range can be extended. So it only costs the cost of a resistor now. It is much lesser than the cost of a meter. So this is a super method. And you have to find in examination point of view, the questions will be asked like, what will be the value of this shunt resistor? That's all. What will be the value of this shunt resistor? So the shunt resistor have the value like, it is equal to Rm divided by N minus 1, where this is the equation, N is equal to I new by I old, because we have to extend the ammeter now. So I new by I old. I new is nothing but, my dears, I new is simply I. So I can write like I divided by I old is nothing but Im. The old value of current it is measured. The old value of current we already measured without extension, without this shunt resistance is called I old. And if you insert shunt resistance, we can measure a very big value of current. That very big value is I, and it is represented by this I. So this is I new by I old is equal to I by Im. Okay, and Rm is nothing but the meter resistance. If you know these two equations, you can directly go for finding the shunt value. So what happens if you increasing, how can we range further you can extend the range. The further extend your range means you have to reduce the value of RSH as possible as. What happened then? If you reduce this RSH to as possible value to maximum, means lowest value of this RSH means more current will be carried by this RSH. The meter is again safe. Suppose you use very high value of resistance here, the meter can't extend beyond some range, because if you add a very high value of resistance here, then compared to meter resistance, a small current will be flowing to this and very big current is again flowing to that. The range cannot be extended at very high length sense to very high level. So for getting very high level of range, what we have to do, we have to add as much as least resistance in parallel with the ammeter. Then we can get maximum possible range of the ammeter. Is it clear? So that is the extension of ammeter. And next, extension of voltmeter. Extension of voltmeter. So see, this extension means, suppose we have a voltmeter. a voltmeter in our hand. Suppose let be V, simply V, voltmeter can be represented simply V. And the meter having certain resistance Rm, there is no change in that meter having certain resistance Rm. And by using this my dear, by using this, we can measure a voltage of Vm. We can measure a voltage up to Vm. Suppose we have to extend this voltmeter means, simply what we have to do, we have to add an extra resistance in series with the voltmeter, so that very bigger voltage you can measure. Very bigger voltage you can measure if you add some resistance in series with the what? Meter. There you add a shunt resistor. Now you have to add a series resistor in series with the voltmeter, so that a very high voltage can be you can measure. Why? Because this series resistor it can itself drop a very high value of voltage, so the remaining voltage will be only available to the meter, so the meter can be safe again. So we can, in total we can measure the total value. In total we can measure the total value. Bus. See, suppose the machine already, the meter already has to what measure maximum 25 volt. You assume. Suppose we have to measure 100 volt, my dears. So what we have to do? This 25 only this machine, but meter can read maximum. So the remaining 75 volt that voltage should be carried by some resistances in series. So what happened? This carries 75 volt. This carry 25 volt. So maximum you can calculate 100 volt. Maximum you can measure 100 volt of voltage there. 100 volt voltage there by using this technique. And here is also what? The value of the series resistance Rd is nothing but Rs is equal to, my dears, Rm into n minus 1. Rm into n minus 1. There Rm divided by n minus 1. Here Rm into n minus 1. Where Rm is nothing but the meter resistance, you know that. Now n will be equal to, so this equation is very important, and n will be equal to V nu divided by V old. V nu is nothing but V, and V old is nothing but, my dears, Vm. So if you know these two equations, then easily you can extend the range of voltmeter also. You can extend the range of voltmeter also. Okay. This n is called the multiplying factor. It's called the current multiplication factor. Correct name is current multiplication factor, and this is n is called the voltage multiplication factor. It's called the voltage multiplication factor. Did you get the idea? Did you get the idea, my dears? Okay. Did you get the idea? Okay. Can we do a question? Can we do some problems? Okay, write a question. A voltmeter having (200 volt) full scale value and percentage accuracy at a full scale is 1%. Find the error at A 100 volt, B 50 volt, C 25 volt. So what is this is a very important question. This is also very important question. A voltmeter having 20 volt, 200 volt full scale value. So write the data here. Full scale reading equal to 200 volt. And a percentage accuracy at a full scale is, percentage accuracy at a full scale is 1%. So you can calculate, we can say like it is an error, right? 1% of error will be there. Percentage accuracy means, it is indirectly it means that 1% of error will be there, right? So you can say percentage full scale error will be equal to 1%. Find the error at 100 volt, 50 volt and 25 volt. Very, very important. So there is an equation, percentage error at desired scale equal to full scale value into percentage error at full scale whole divided by desired value or desired scale. Desired value, okay, desired value. I will tell you by using this example. Okay, first of all 100 volt A, 400 volt. Listen. So listen, a voltmeter or an ammeter, any meter, it having certain, see, this is the meter, of course this is the meter. So this is the meter, my dear. So this is the point, right? This is the point. So the meter having certain error at its reading due to many reasons. It may be due to spring tension loss, it may be due to the measurement problem, it may be due to the magnetic leakage, anything. So due to anything there will be some error. And how can we find that error? Suppose the error is already given, the meter, it is a guaranteed accuracy error actually. That guaranteed accuracy error means the meter owner, or in the sense the meter manufacturer itself is saying that, array, this meter having this much error, so you have to compensate for that error. They already tell to us these are the error. That is called a guaranteed accuracy error because it's always constant. It depends upon the full scale reading. I already told you. So a voltmeter having 200 volt full scale value, so its maximum value is nothing but, my dear, 200 volt. And a percentage accuracy at full scale is 1%, means when it reads 200 volt, there will be 1% what? Error. That is the meaning of that. Find the error at 100 volt. Then at 100 volt, what will be the error? Whether it will be same 1%? No. That is equation we used there. Percentage error at desired scale means at any scale rather than this 200. That is the meaning of desired scale, which is equal to full scale value. So it will, so percentage error at 100 volt, which is equal to what? Full scale value. What is the full scale value? 200 into what is the full scale error? It is 1%, correct? Divided by what is the desired value? We have the desired value of 100. For 100 value we have to calculate, so it will become 2, so it become 2%. So what is the conclusion from that? The meter having a least error at its full scale reading only. For lower values of reading, the error will be what? Proportionally increasing. For 50% of the reading, the error is double. The error is double. Is it clear? So next, what? For 50 volt, what? Next, for 50 volt, how can we find that? Percentage error at 50 volt will be equal to what? Full scale reading again into full scale error divided by 50. So it become 4%, my dears. It become 4%. See how much it is increasing. For 1 by 4 of the full scale value, the error is 4 times increasing, my dears. So for 1 by 3, 3 times increase. For 1 by 5, 5 times increase. Is it clear? Is it clear? So that much difference will be there in terms of the error. So see, next value for 1 by what? 25. 1 by, see this one, 25 volt. Let's see that for 25 volt. For 25 volt, what will be the error? So percentage error will be equal to what? Full scale reading, there is no change in that. Full scale percentage error, there is no change in that. Desired value is 25. 8%. See, 25 means 1 by 8 of the full scale value, my dears. So for 1 by 8 of the full scale value, if you measure, that means the lower the value measure, the higher will be the percentage error. The higher will be the percentage error. That is the conclusion you obtain from this. Is it clear? Is it clear? So any error you can find for any desired value you can find by using the equation. Percentage error at a desired scale will be equal to full scale value into percentage error at full scale divided by desired value. Okay. Is it clear? Is it clear? This is a very important problem. Is it clear, my dears? Is it clear? Okay. Write another question. Here 0 to 250 volt voltmeter. Here 0 to 250 volt voltmeter has a guaranteed accuracy error. Guaranteed accuracy error of 1%. Of 1% of full scale reading. The total voltage measured by this instrument is total voltage measured by this instrument is 100 volt. The limiting error will be what? So same equation you can use here. What is that? Percentage error at desired scale is equal to full scale reading. What is the full scale reading, my dear? 250 volt into what is the guaranteed accuracy error? Full scale error 1% divided by at what voltage we have to find? For 100 volt we have to find. So this much is the error. This much is the error. Is it clear? Is it clear? Write another question. 0 to 300 volt voltmeter has an error of 0.001 plus or minus 2% at a full scale deflection. Full stop. What is the range of reading? What is the range of reading? If true voltage is true voltage is 30 volt. How can we find this? So what is the range of reading if true voltage is 30 volt? Okay, this much error is there for full scale. Then for 30 volt, how much will be the error? So that what will be the range of the instrument for 30 volt? Okay, so again percentage error at 30 volt will be equal to what? Full scale error reading, again 300 into 2% divided by 30, so 10, so 20%. So 20% error will be there at 30 volt, which means 20% of 30 will be equal to what? 6 volt, correct? So there will be plus or minus 6 volt change or error in 30 volt. That is, the range of meter will be 24 to 36 volt. Am I correct? Plus or minus 6 volt changes will be there, which means that plus or minus 6 voltage changes will be there, my dears. So 30 minus 6, 24, 30 plus 6, 36 bus. That's all. That's all. Is it clear? Is it clear? Care of this? Next, errors. Type of errors. This also, no, it's very easy actually, but there are some questions related to this usually asked. Type of error. There are 3 types of error, my dears. Gross error, systematic error, and random error. And again, systematic error classified into instrumental error, environmental error, observational error. Instrumental error, environmental error, and observational error. So let's see one by one. Gross error means it's a man-made error. It's a man-made error. That means, suppose in your laboratory, you assume you already did that in the laboratory now. So in the laboratory, suppose 5 persons are there, and one person is what? Adjusting the machine, and one is taking the reading and they say louder, okay, they say louder, and one is noting the reading, So suppose a person is saying 23.8 ampere, but due to some reasons, so due to some mood swing and all, right, the listener, they heard like 28.3 ampere. There they occurred an error. This error is not due to the machine, this error is not due to the reading, but this error is purely based on what? Purely based on the listener, the mistake of the listener, So this type of error is due to the man-made error. So gross error is nothing but the man-made error. The error due to what? The person who is taking the reading. That is called the what? Gross error. Next, systematic error. So gross error means it is not following anything. It is simply what? Random manner. So suppose this reading same can be, suppose in his hand, in his eye, it may see like 28.8. Then also there will be error. So it is not following a system rule, following not a systematic rule. But in systematic error, my dears, this error follows certain specific rule. Rule or law. Specific rule or law. I will tell what it is. First of all, instrumental error. Instrumental error means it is the problem with the instrument. For example, when time passes, the tension of the spring, suppose they are using spring constant, spring control mechanism, the tension of the spring, right, it may weaken. It may weaken means there will be an error. That error will be constant. That error follows a certain rule, because the spring is weakened by certain factor. So that much factor error will be there in the reading, which means that error follows a certain pattern. If I took the same reading, then and you took the reading and he took the reading, every time, at the 3 time, the error will be same. It is not changing with respect to person. That is called, it follows a specific rule or law means. So instrumental error means is a problem associated with the instrument. It's a problem around with instruments. So permanently, see, suppose we bought a new instrument. We didn't set it 0 setting. There is normally in the laboratory, as a first step of doing every experiment is that we have to set the 0 of the voltmeter, ammeter and wattmeter. Because due to the operation, there may be less than 0. The pointer exactly 0, parallel with the 0 before taking reading. But due to some reason, it may not be at 0 or it is away from 0 in forward direction. So we have to make it back to 0. So for that, there will be a screwdriver. There is not screwdriver, there will be screw. So this is our meter. So there will be a screw here. And by using a screwdriver, we have to adjust the needle so that it will come to 0 initially. So that is called instrumental. So instrumental error means the error associated with the instrument or the measuring device is called the instrumental error. That we can't avoid, right? That we can't avoid. Only we can avoid that effort of error by calibrating the instrument. Next is environmental error. Environmental error means these are the electrical instruments. So its resistance value now, where inside we are using winding, inside we are using what? Magnet and all. So what happened, my dears? Due to the temperature variation, the winding resistance may vary. So if suppose you are taking the instrument reading at now, suppose the room temperature here it is say 30 degrees Celsius. Suppose you are going outside or the exterior of your building and you are taking another reading. Suppose the outside temperature is 40 degrees Celsius, then the reading will not be same. It will vary because there will be a factor of environment effect. There will be a factor of temperature effect. Or suppose the humidity also, it can be also affect. And suppose you are taking reading with nearby some magnetic field is there, so it will affect the internal magnetic field of the meter. So there also there is a chance of what error. So the type of error is called environmental error. This type of error is called the environmental error. Okay, another type is observational error. Very importantly, it is called the parallax error, my dear. Parallax error, which means in your laboratory, see, this is the scale, this is the scale. Okay, so this is the scale, and actually here the pointer lies. Here the pointer lies. So you have to make sure that you can't take a reading by this way. Okay, 10. You can't take reading by this way, but you should take reading by this way. You exactly what upper or above the what needle. Then only there will be a parallel between the needle and the reading value. This error, suppose this is not there, suppose you are here, the reading will not be here. You are there, suppose you are taking the reading from there also there will be error. This is called parallax error. So for avoiding that parallax error, there is always some mirrored scale, my dears. Mirrored scale. So mirrored scale means beneath the or side of the scale there will be a mirror, so that the needle reflection, it will be exactly on the mirror. So that you can conclude, okay, even though if you look it from this side, the reflection takes the correct value. So you can directly go to the reflection and take the value, no issue. So at that time you need not be always at the top of the what needle. You can take reading from here, you can take reading from here, because the reflection is already on the mirror. You just see the reflection, not the needle. So in that way you can avoid that type of error also. Okay, so that is called an observational error. So I already told you, follow specific value or rule means it having certain constant error. That is why it follows specific rule. Next one, random error. Even though we completely avoid this instrumental error, environmental error and observational error, we perfectly make the instrument, an AI instrument, a new instrument, a brand new instrument, which is manufactured by a super #1 company. Even though then also there will be a chance of some errors. This error is not classified, this error is not identified, but there is some error. We know that there is some error. That error is called the random error, or the unknown error in the measurement is called the random error, my dears. Unknown error in the measurement is called the random error. Okay, so these are the type of errors. These are the type of errors. Okay, write a question. Write a question. A moving coil ammeter, MC, short formula MC ammeter, having an internal resistance of having an internal resistance of 50 ohm and measured 100 milliampere. Find the value of shunt resistance. For measuring 1 ampere. What is that? A moving coil ammeters. It's an MC ammeter, right? Having an internal resistance of 50 ohm, which means the meter resistance is given as, my dears, 50 ohm, and measured 100 milliampere. So it measured, normally it measured the meter current. It measured the meter current. That means if you draw the rough figure, so the meter resistance Rm is equal to what? 50 ohm. It normally measures a current of what? 100 milliampere. So find the value of shunt resistor for measuring 1 ampere. So if you add some resistance in parallel, that's called shunt resistance, then you can measure more value of current. That current is nothing but 1 ampere. That current is nothing but 1 ampere. So Im will be 100 milliampere, or I will be, you have to measure like 1 ampere. So what will be the value of RSH? We have RSH will be equal to, my dears, what? Rm divided by n minus 1, and n is equal to I new by I old, or I by Im, which is equal to what? 1 ampere divided by 100 into 10 raised to minus 3. So it will become 10 raised to 3 by 100. So it will become 10. Multiplication factor na 10. No unit, right? So RSH will be equal to what? Rm is nothing but 50 divided by 10. So 5. Sorry, 10 minus 1 na? 10 minus 1. So it will be 50 by 9. So this much resistance will be added in parallel with the meter. Then you can measure up to 1 ampere. You can measure up to 1 ampere. So 50 by 9. 50 by 9. Is it clear, my dears? Is it clear? So that's all for today's session. So let's meet again tomorrow with new session. So until then, bye. Take care.